Anyone? No? Like you got no questions if you didn't do anything, right? uh. Do you all know where the practices are if you need more practice? Yeah? I don't want to make my lessons a practice session. So if you don't do practice, right, then that's kind of like on you. Because I need the time. I only have one lesson a week. If you want me to hold an extra practice session, I actually do sometimes do that, right? Especially with this like kind of like this size of a class. But I'll usually do it like on a at night, one of those like weekday nights, and then I just get everyone to log in. I just give you something to do, right, on a Saturday. Then on the following weekday, I'll just tell you all, I'm gonna go through these questions, right? Because the lesson here itself is best used when I'm doing the lesson and the practice. I don't want you to sit here and do practice. If I sit here and see you do practice, right? That's just me doing this all the whole time, right? You've seen the examiners, the invigilators, right? You go for test before, right? As you're doing the test, what's the invigilator doing? Like that, right? That's all they're doing, right? I don't want to spend my time doing that. I feel very uncomfortable doing that, right? It's like, what? My head just bobbing the way all the time, right? Okay, so you have to go and get the practice done at home, right? So if I need to have a practice session, I will hold an online practice session, right? And I'll go through the questions, right? So it's like, oh, I don't know how to do this one, I don't know how to do that one. That's fine. If you don't want to let people know that oh, Sam's gonna call me out during the session, and then like everyone's gonna know what I got wrong, then then it's fine. Just DM me and then say that I need to go through these questions anonymously. Then I'll just go on the online Zoom and say like, oh, I got a request for doing this question, that question. Right? It's fine. Okay? Right? Nobody's gonna judge you. Right? Only me. Right? Even then also I don't judge you. I know that you guys are struggling with this, right? So it's fine. Okay. Um. Let's. Oh no, the printer just stopped printing because I think it's run out of paper. But okay, a few pieces here. Nope. Well, the printing is not done. Okay, all right. Just a little while more, we can get started already. Sorry for the delay. Oh no, wait, what's going on? Oh. Okay, sorry, I think I'm messed up. There's a repeating copies there. Pass to the back. I need to check whether it's correct. Okay. Sorry, this you're supposed to take one step. Okay. Yeah, take your copy and then pass the rest on. Okay. Have you done this in chemistry? You have, right? Okay. Cool. Oh, you don't have? Hey, pass back one copy. There should be spares here. Okay, you done this in chemistry, right? Regular arrangement, disorderly arrangement, and all that. So here's the thing. So what's the difference? There are slight differences, or maybe I just want to point out some things that you have to pay attention to. So we start off by talking about this first, right? So I'm gonna assume that you're doing chemistry. Okay, that assumption is okay. That assumption is valid. Okay, good. So if I assume that everyone's doing chemistry, right, then everyone should understand here. So I'm just gonna touch on some important points. When you draw a model of liquid particles, right? When you draw a model of liquid particles, a very common mistake that students make, right? A very common mistake that students make when you're drawing liquid particles is, right? They might draw it separated like this. Okay, this is not a liquid. This is a. So for liquid particles, they still must be touching each other. Right, so they must be touching each other still. So you have to draw it like this. Okay, right? You have to draw it like this. So it has to be touching each other. I mean, that's the case of like how I drew my diagram here. The next common mistake that students make, right, it's not really a mistake, but more of like a disadvantage that you do for yourself, is that you start to draw really tiny little particles like that. You start to draw like this. Okay, right? When are you gonna draw? Until the end of the exam, is it? Right? No, right? So please make sure that you draw a little bit bigger. Right? Nobody's saying that it has to be drawn smaller or bigger like this, right? So make sure you draw it a bit bigger, disorderly and still touching each other. So because of that, let me ask you this: what's the intermolecular forces? I want you to compare the intermolecular forces of the particles for liquids. Is it strong or is it weak? Right? The answer is relatively strong. Okay. All right. So it's still relatively strong. So the intermolecular forces is still relatively strong. Okay. That's the key phrase that you should be using. That means it's still strong, but not as strong as solids. Okay. And it's definitely better than gases. Okay. Give me the intermolecular forces. Like specifically, what are they? What forces? What are the intermolecular forces that we speak of in chemistry? Yeah, the attraction, but specifically what are the names of these attraction forces? For you, you'll be learning London dispersion forces, right? Oh no, or van der Waals. Yeah, van der Waals. Okay, so you never heard of London dispersion. Okay, that's fine then. Right, so van der Waals. Right, van der Waals. Is van der Waals attractive? Or is it repulsive? Or is it can be both? Only attractive. Any other intermolecular forces that you may get? Other than from van der Waals? Anyone else? Let's see how good your chemistry is. This shows you how in-depth your chemistry is, you know? Like how deep your knowledge of chemistry is. What other kinds of intermolecular forces could you get? Molecular. So electrostatic forces is not considered intermolecular, right? Those are interionic forces. right? Wow, chemistry must be so specific also. Yeah, of course, everything has to be specific. Hey, any other intermolecular forces? Anyone heard of this? Polar forces? Like some molecules are slightly polar, like water is slightly polar. Have you heard of that before? Wow, what happened to your chemistry here? Huh? H2O, if you draw the H2O molecule, did anyone say that? Did anyone tell you that this is slightly negative here and this is slightly positive there? No? What kind of chemistry you all doing nowadays, man? Right, but it is, huh? Okay? Right, this is part of the reason why water can exist as water, because like this is the molecule, but it's slightly polar, so it's slightly negative here, slightly positive here, so they kind of like attract each other. So water molecules tend to remain as water for quite a while. Yeah, so this is what they call dipole attractions, right? Dipole attractions. Any other kind of intermolecular forces that we heard of? Heard of hydrogen bonding? Anyone heard of hydrogen bonding? Please tell me you heard of hydrogen bonding. Never heard of hydrogen bonding? Ah, chemistry you're doing Okay, it's pretty much still there one okay. So van der Waals, dipole-dipole, as well as hydrogen bonding are all examples of intermolecular forces. But I think my point is this: they are all attractive. There's no such thing as repulsive forces. There's no such thing as, oh, this particle will repel another particle. It's all attractive. You know what I'm saying? So obviously for solids, they have the strongest attractive forces, therefore it's hard to pull them apart, right? For liquids, it's relatively strong, and for gases, it's weak. So it's easy for the particles to move around, right? Because all the forces that we talk of is attractive. Okay? Now in physics, we can just call it intermolecular, right? If you do that in chemistry, they will penalize you. You're aware of that, huh? Can I use the word intermolecular forces for helium? Can I say that, oh, helium gas particles experience intermolecular forces? Can I say that? Why not? Because nope, that's not it. Anyone? Helium. Why can't I use intermolecular forces for helium? I'm just giving you a bit of heads up for chemistry lah. What do you think? Right? I only focus on physics. I used to teach triple science. I know the pitfalls everywhere for all the subjects. Intermolecular forces. Can I use it for helium? Why? Still why cannot? What's helium as a gas? It's a monoatomic gas, right? It's made of atoms. It's not made of molecules. So you cannot say intermolecular forces for helium. That's the reason why. If you want to say interatomic forces, that's okay. But you cannot say intermolecular for helium. Do you understand the difference between a molecule and an atom? Say yes. Say yes. The answer is yes. You have to know the difference between a molecule and an atom. You need to know the difference between a mixture, an element, and a compound. Okay? I leave that all to your chemistry teacher, none of my business. Okay? But in physics, we can call it intermolecular forces. That's fine. Okay, so I'm trying to say that, in physics, we don't really care. In physics, right, be it helium, be it don't know what, right, what element, or be it what compound, or what molecule, all the same, intermolecular forces. Can Okay, good. So the idea here of this thing called kinetic particle model, right, maybe you want to just kind of like, box up the word model. Why is it called model? It's called, okay, there are many names to this thing. They call it the kinetic particle model, they call it the kinetic model theory, they call it the kinetic particle theory, they call it the kinetic particle model theory. What does a theory mean? Is it just a theory? Just a theory means that it's been proven already. The word theory means that it's been proven with evidence. That means it is absolutely true. So if you say something is just a theory, it means that it's true. What you meant to say that it's just a hypothesis. So if you see the word theory in physics, right, it actually means that it's the real thing, right? It's been proven. But the thing is this: why is it a model? Exactly, because we can't actually see it, right? We use the word model because there's no way that we can ever see, right, gas particles. There's no way we can ever see liquid particles. I mean, we've had to some extent some successes in the recent years, like maybe only last year, with some very specialized microscopes that we can see solid particles arranged like that, right? But we still can't do that for liquid and gas because they keep moving around, right? Okay, so no matter what, it's still a model. Now, how do you know that this model is true? I just said that it's a theory, right? Theory means what? Yeah, it's been proven it's true. So how do we know it's true? If you can't see it, how do you know it's true? This is not faith. Huh? It's got nothing to do with that, okay? All right. So how do you know it's true? I just believe. No, it's not that. Okay. So we know that it to be true based on experiments. We know that this is true based on experiments, and the most basic experiments that you learn is this thing called the Brownian motion experiment. This one, right? Which I'll touch on later. But here's the thing. So I want you to understand that all these things that you're learning now, what molecular arrangement, how they move, and the types of forces between them, all of these are all proven theories, but they are based on a model, right? Someone thought of it, someone sat there and just started thinking about it like, this is the best explanation that we can come up with. Otherwise, we won't know, what this is all about. Can? Okay, good. So, what's the other properties of solid, liquids, and gas? What are other properties of solid, liquid, and gas? What do you have? You have the shape, density, volume, compressibility. Yeah, this one primary school you all do before already, right? You know why I know it's this one you do in primary school? Because I got a primary 4 kid, right? And he's doing this in science now, and he's failing in science. I'm sorry. He's not failing, he's just not getting his A, right? So he needs to learn how to explain the things, and I'm always not there to teach him how to explain. I mean, I'm trying to make time for him now, but yeah, okay. My wife, on the other hand, is a very arts person. She's not very sciencey, so I mean, maybe I should have taken it on a bit earlier. But anyway, so my job here is to tell you this. It sounds like primary school, but it's not in secondary school, because you need to talk about the molecules. So you're one level up lah. I mean, if I ask you this, all right, it's a shape of a liquid fixed. Then you tell me not fixed. You think you want mark like that? No. You have to explain why. You have to explain in terms of molecules. Why? Because the molecules are free to move about. So it will just take up the shape of the container. Can? Do you remember primary school? You didn't learn about molecules. Like in primary school, they never mentioned like your answers must be in the form of molecules. Don't have, right? You just remember that liquid, right? Shape, not fixed. Okay, can. That's good enough, right? PSLE, right? But now secondary school, you need to talk about molecules. Talk about molecules, talk about molecules, talk about molecules, talk about molecules. Every other thing you have to mention about the molecules. Right? You done it in chemistry, right? Yeah? Okay. Right, so I'm not gonna harp on this too much. I just want you to remember that every time you talk about this chapter, when you're writing, right, you must write it in molecules. Okay, one thing though, there are no equations here. This chapter has no formulas. There's no force and distance. There's no mgh. There's no half mv squared. You're like thinking, wow, shook, no equations. You have to write everything down. You have to describe everything in a sentence or 2 sentences. Alright, I hate these kind of chapters. I truly hate these kind of chapters. You know why? Because most teachers will just say that, you all know this one lah. You all done this in chemistry, right? Skip. Go to the next chapter already. Right? Then all the phrases, So I want you to understand one thing about my notes. My notes are written in such a way, especially for these kind of chapters, right? The phrases are written in such a way, you see a lot of words, you can fall asleep, right? But they are written in such a way that if you need to write down an answer for a question, right? The phrases are exactly what you see in here. Okay, it's already been written like that already. All right. Because the last thing I want you to do is go to exam, sit down there, and then start thinking, how do I answer this? How do I answer that? They ask me like, why is the shape of a gas not fixed? How do I answer that? So by the time you try to figure that out, end of exam already, right? You wasted your 1.5 hours. Okay, all right. So you got to memorize the phrases. That's the tough part. All right. So if I ask you to memorize the phrases, you will tell me, all right, I'll do that next week. Then I ask you next week, you say, I'll do it next week. And next week, after next week, guess what? 2027. Right, your exams are over already. Right, you're in wherever you are in already. I don't know where. Right, so don't wait. All right, spend time to memorize these phrases, especially after the class or maybe during the week itself. There we go. I think one thing is very like the thing that I always see students getting wrong, right, will be this one here. Right, for liquids. Okay, for liquids, the volume is fixed. Right, for liquids, the volume is fixed. So the question is, what do they mean by that? What do they mean by the volume is fixed for liquids? What do they mean by that? Means that if you have two containers, right? This one's a 1 liter container. This one's a 2 liter container, right? So if I fill up this thing with 1 liter of liquid and I pour this into a 2 liter container, then the liquid will fill up to 1 liter. Like, it won't fill up the whole thing, right? Okay, so that's the idea for liquid. So liquids, the volume is fixed. The shape is not fixed, but the volume is fixed. You understand this? So the shape will take on everything, right? Okay. The tough part is the gas one, right? What does it mean for a gas volume to be not fixed? Okay. So imagine that I have a pump. Let's say imagine this is a pump, right? Instead, right? So there's a pump here, and I'm pumping gas into this cylinder, right? Everything is airtight, right? And I'm pumping gas into it. Like, what's the volume of this thing again? 1 liter, 1000 cm3, right? Let's say I have 1000 cm3 of gas. You done gas in chemistry already, right? Mole concept, we done that. Molar gas volume, all that, right? So let's say I squeeze this gas, I compress this gas, I push this 1 liter of gas into this container, which already had gas. Okay, right? Like, how much gas is inside this container already? I mean, I removed the stopper. How much gas was inside? 2000 cm3, right? So if let's say I compress, I push this amount of 1000 cm3 of gas into this container, and then I trap the gas inside. What's the new volume of the gas inside? It's 2000. That was a trick question. There's no new volume. It's still 2000. Okay, right? Why is the volume the same? It's a rigid container, right? It can't expand. So even though I have squished, right, a certain volume of gas into this thing, the volume still doesn't change. The number of particles is more now, but we can't see it, right? You can't see it anyway. Okay, it's more. There's a greater number of particles, but the volume depends on the container. Likewise, I can do this also. You see, 2000 cm3 of gas inside. Okay, I put it to a pump, and I suck out some gas. Let's say I suck out like 500 cm3. And then after I remove some gas from inside this thing, and I cap it like this, right? What's the volume of gas inside now? Still the same, 2000. It doesn't change. So whether you have more gas particles inside or less gas particles inside, gas will just fill up the entire container. Okay, so you can have more gas particles, right, in the same volume, especially if your container can't change volume. So what kind of container can change volume? Like, is there any container that when you pump air in, the thing will become bigger? Yeah, like a balloon, right? A balloon will increase volume because it's elastic. This is not elastic, right? It's a rigid container. Okay, so just take note that, right, when we are dealing with these things now, you look at the container. If you know the container can expand, that means the volume can change. If you know the container is rigid, then the volume cannot change. Okay, no issues here. Okay, good. Okay, then the compressibility and all that kind of thing, I'll leave it to you. But liquids are incompressible, Why? Because there's very little space between the particles. This is where some students will then say that, hey, but if you say very little space, right, then I'm looking at this. Got space what? Right, got space what? Guys, this is just a sample drawing. In fact, there's more particles than this, right? All of them are just squished to each other, right? We have to try to draw the disorderliness, right? But yeah, we have to remember that liquid spaces are very, very little. So liquids are incompressible as well. Okay? Right? What if they ask me a trick question? What if the liquid can compress? Huh? Yeah, that's not right. Like, teacher's not right in the head. No, really, legit. Right? Because some teachers try to be extra. They try to be special. Okay? Yes, there are some compressible liquids in the market. Right? In real life, there are some compressible liquids, but in your syllabus, they are all incompressible. Okay, on this? Okay. So kinetic particle theory tells us that, right, even though we can't see the molecules, we still can get an idea of how it looks like and how they behave. Right? This chapter, whenever you write an answer, it's all about particles. Particles, 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 particles. Everything, right, about particles. The gas particles. How the gas particles move in. How are they packed? What are the forces between the gas particles? Any issues on that? No? Okay, so don't make a mistake though, right? Even though I say all this, I still will see some students still making mistakes because of your preconceived notions, right? The best thing to do is for you to practice. All right, there's this experiment called Brownian motion. Brownian motion, okay? This is new to you, so I guess this will only like really make sense when you're in school. So I'll tell you what you need to know. Then when you go to school, they tell you what it is. Then you will kind of like put one to one together and then realize that, oh, okay, that's why this is important. Okay, all right. But I'll tell you what you are like. Most students are usually confused by. So a bit of backstory, a bit of a history lesson. Okay. So Brownian motion, the guy who discovered it, I'm just guessing his name was Brown. Yeah. Do you realize that all the units are all someone's name? Celsius is someone's name, Kelvin is someone's name, meter is someone's name. Like they're all names, you know. Yeah. Like force is in newtons. The dude is Newton. Pascal. Yeah. Yeah, they're all names. So Brownian motion was by some guy called Brown. But he was a botanist. Yeah, he's a botanist. He wasn't a physicist. Botanist are someone who studies botany. Plants. Yeah. So he was looking at pollen grains under a microscope. Think about that. Pollen grains under a microscope. Okay. You are the lab assistant. Prepare the microscope slide. Pollen grains on a microscope slide. What do you have to do? You've done this in science, right? Sec 1, Sec 2 science, you used a microscope before, right? You prepared the glass slide before, right? Yeah, you have, right? So what are you supposed to do? Glass slide. Sprinkle the pollen grains on it. What paper thing? What paper? No lah, what paper? Okay, so the pollen grains are on the glass slide now. What do you do? Hey, you done this in Sec 1, Sec 2 science. This one requires a little bit of prerequisite or no? If not, how they allow you to take physics? Or chemistry? No lah, not so fast. You need water. Right, so the idea here is you put some water, then you put the cover slip on top. Right. Hey, need to give so detailed steps, man. Need to give or not? Need. You know why? Because all your practicals all got planning. Yeah, you have to describe the planning steps. Okay? I'm the messenger. I'm not the one who make the rules. So you put a cover slip on top. So do we understand that the pollen grains are surrounded by water?
Yes.
Can you see the pollen grains?
Yes.
Can you see the water molecules?
No.
Cannot, huh? So pollen grains can be seen. Water molecules cannot be seen. Okay? So I'm just gonna describe to you what he saw. Right? That's what Brownian motion is. Right? Describing what Professor Brown saw. And so under the microscope, he looked at the microscope. And then how does a pollen grain look like? It looks like actually it looks like coronavirus. Yeah, this is a pollen grain. Okay, so he saw many pollen grains inside. Okay, and is it surrounded by water? Huh? It's surrounded by water, right? Can you see the water? Cannot, right? Okay, good. So this is what he saw under the microscope. You get this? Can? Anyone been to the science center when you were in primary school? Primary school at least got go once or twice. Got go once science center. At least got like your excursion got bring you, right? At least, right? Do you ever look into a microscope before? Did they show you a microscope there? Okay, there's an exhibit there. It's super old. How do I know it's old? Because it's been there since I was in primary school. It's the same setup. Like there is a microscope set up in one corner of the science center. You know the open area where there's a lot of experiments going on. Like at one very hidden corner, there is still one microscope that's placed there, and there is still a slide on it with water in it and pollen grains on it from the 1990s, since my time. And it's been there. It's encased in plastic. You can only look at it, the eyepiece here, and you will see the exact same thing like this. Right? That was an experiment. That setup is to show Brownian motion. Okay? So what did Brown observe? He observed that the pollen grains were moving around randomly. Like when he just observed one of the pollen grains, even like he could isolate one of the pollen grains, he observed that the pollen grain was moving around randomly, and it didn't stop moving since 1990s until now. It didn't stop moving. Now, does it make sense? Does it make sense that it's still moving? Like why would it move?
Yeah.
No, it's not gas. Pollen grains. Pollen grains is a particle. It's like a speck of dust that's on the table right now. You look at a speck of dust that's on the table. That could be a pollen grain, right? Or maybe the eraser shaving there, right? That's like the size of a pollen grain. Do you understand that? And should it be moving? It's trapped under a cover slip. The water is not moving. Everything is not moving. You understand what's the issue now? The issue now is everything's been sealed. There is no wind blowing over. There's no chance of anything like moving, like making it like flow or anything like that. It's not tilted. It's sitting on the table. Nothing's moving, but the pollen grain is doing this random path. Do you see how? Do you realize that that's the problem? Like, why is it moving? Yeah, why is it moving? How do you explain someone like oh, the pollen grains are alive? Since my time has been 30 years, anything under the cover slip would have been dead already. Like long gone dead. So the pollen grains are just like just plant material that's like if it's been soaked in water for too long, it's definitely dead lah. So why is it moving? It's surrounded by water, right? It's surrounded by water. There are water molecules around, but you can't see water molecules, so I'm not going to draw it in. So maybe I just like there's water molecules around. There's water around everywhere. So why is it moving? Why is it moving randomly, right? All this time. Okay, so the answer is the idea here is this: it is moving. Huh? Brownian motion tells us that he observed that the particle, the pollen grain, was continuously moving and randomly moving, non-stop. Okay? And your job is to explain why is it doing that. Right? Do you understand that it should not be moving, but it is? Right? And it doesn't stop moving. So it's continuous moving. Okay, so imagine you're Professor Brown and your job is to explain to his boss why your pollen grains moving. How are you going to explain? Sweat now. Fella must be sweating, right? Cover slip covered already. Water is there, right? Pollen grain is moving. Then the boss is asking you, why your pollen grain is moving? I want it to stay still. If you want me, if you want me to, if you want it to stay still, I will use glue lah. I'll just use resin glue and then glue it there, right? But when I use water, these particles start moving around randomly. Right? It's because of the water molecules. So Brown, the guy had to come up with an idea. He had to explain. So his idea is this: maybe the water, right, is made up of small water particles, and maybe the water particles are colliding with these pollen grains and causing the pollen grain to move around randomly. So the water particles are just kind of like bumping into it. You know what I'm saying? Right? Causing it to move around randomly. But you know what? Can you see it? Can you see it? Cannot. Why cannot? Too small, right? So the idea here is this. So Brownian motion had to come up with a deduction. So he deduced that the pollen grain must have been colliding with some invisible water molecules. And the very fact is that water is made up of these particles. Right? Water has particulate nature. Okay? It's not like one fluid thing. It's like made up of tiny particles. And the tiny particles are colliding in the pollen grains. Okay? So a pollen grain is a very big object. You can see under a microscope. A water molecule is a molecule you cannot see under the microscope, right? So we had to deduce that water molecules are colliding into the pollen grains. Okay? Anyway, so what's the three things for Brownian motion? Long story short, okay, long story short, because this is history lesson. Everyone hates history. I hate history, right? Number one is the observation. If you're asked right, if you're asked to explain what Brownian motion is, you write this down. Number one, what do you observe? So what's the thing that you observe? He observed the pollen grains moving continuously and randomly. These are your key phrases. Right? That's the observation. All right. Let me tell you this. If I don't say it, if I don't tell you, if I don't mention it, you know what you're going to write down? You're going to tell me that Brownian motion observed that the water molecules are moving. Does it sound right? Actually, it sounds suspiciously okay, right? He observed that the water molecules are moving. But you can't observe water molecules. So the moment you write that, you will be struck down already. And then you'll be thinking that, oh yeah, I'm going to get it right. No, you're not. You're going to lose a mark. Okay? So you cannot, absolutely cannot write that water molecules are moving. Right? You cannot say that you observe the water molecules are moving. Okay? So what's the second thing? Second thing is that you deduce. You can't see it, so you got to deduce it. You got to infer that the water molecules are bombarding the pollen particles continuously and from all directions. And then you deduce again. So 2 deductions. Right, that the water molecules must also have been moving in continuous random motion. And this is understood to be the Brownian motion. So once you get Brownian motion question, is these 3 standard phrases. What do you observe? What you deduce? What you deduce. Right, I've broken it down as simply as I could for you already. And I've given you very clear instructions on how to get the marks for this already. Right, so once you get this question, ask you, explain what Brownian motion or explain what was observed during Brownian motion and explain why he observed that. 1, 2, 3. There's nothing that deviates from this. Okay? Next week, then I memorize lah. Then next week, then I memorize lah. I'll just memorize it the day before exams because that's the best. Like, you will tell me that, oh, that's my best study method. Nah, that's not your best study method. That's your best lazy study method. Right? You're just trying to clutch it only. What are you going to try to do? Memorize everything. How many chapters you have? Right? We are on the what? Chapter 7. Dude, you got 20 chapters, man. End of year is how many chapters tested? I think at this point 10. Some of you 9. I think Garen is like 11. Yeah, you have 11 chapters tested. Right? Don't leave it all the way to the last. Try to memorize it now. Right? Oh, but my church said, my school church said I'm not supposed to memorize things. Do you not memorize your national anthem? You memorize it, do you understand it? Do you know how to translate it? You don't, right? You memorized it, right? How? You sang it all so many years. Same thing, sing this song. Right? Right? Sing this song, repeat the lyrics over and over again until you get it into your head. That's the way to do it. Right? Go and memorize your solubility table. Oh. Go and memorize your preparation of salts. Oh. Right? Those are the 2 most important things for the whole of chemistry. If you want to ask me what's the one thing that's causing your chemistry to suffer, it's because of those 2 things. Right? Those 2 things at the start of the year, solubility table and preparation of salt. You get these 2 things wrong, you're going to get the rest of chemistry wrong. Right? And your chem bonding as well. So if you have to, go and revisit those chapters. Force yourself to memorize those 3 things. Chem bonding, separation techniques, right? Preparation of salts, as well as 4 things are in total. Right? As well as solubility table. That one thing is like so important, dudes. You have no idea. You really have no idea. I think any teacher, any chem teacher that's trying to keep it right and keep you at the lessons, right, keep you running for lessons because they don't tell you that those 3 things are the most important things, right? That will either make or break your entire chemistry. Yeah, you didn't realize that? Nobody told you that. Chem bonding is like number 1 most important chapter. You mess that up, you're not gonna do well for the rest of chemistry. Yeah, if you tell me that, oh, I'll try to cope. Nah, dude. I know, yeah. I've taught chemistry before. I've done this before. You think I've never done this before? Right, what, middle of the year, Sec 3? Right, they moved on to other chapters. Like what are other chapters now? What are you doing for chemistry now? Oh, okay. Anything later than that? You also won't know, right? There's this other thing like air environment and all that also. Right. Yeah, I just go back to the first 3 months. I said, like, if you want me to teach you, I have to go back to the first 3 months. I'm not going to teach you whatever you're learning now. Preparation of salts, your chem bonding must be solid. your solubility table must be solid. So I'll just keep on testing on every week, right? Start the lesson, half an hour, solubility table, write down the whole thing. Yeah. Chem bonding, give me all the formulas, all the radicals, give me all the charges and all that also. That's how you do well for chemistry. For physics, let's say you mess up pressure. Let's say you're bad at pressure. Let's say you don't know how to do the barometer. What's it got to do with this? Physics is modular, that's okay. Right? But it's just a lot of things to learn. Right? But seriously, man, wow. The chemistry, the first 3 chapters are like the most important ones. Okay, so there's this thing, if you notice, I keep talking about this, I added on this thing here, right, about smoke particles. Smoke particles. Okay, so I'll describe to you another experiment, same thing, but it's a different setup and it's a different observation. Okay, right, somewhat different. So for a smoke cell, it's basically a box with smoke particles in it. Okay, what smoke particles? How do you get smoke particles, guys? Huh? No. What's a smoke particle? Let's say I want you to make smoke. How do you make smoke? I'm not asking you to smoke. I'm asking you to make smoke.
Ice.
Nah, that's not smoke. That's water vapor. You want to burn something, right? Yeah, but I'm not going to do it here. You understand, right? For safety reasons. Okay, so if you burn something, you get smoke particles, right? Okay, if you burn something, you get smoke particles. Like, what's the worst case of burning something and getting a lot of smoke particles in Singapore? What's the worst case have you seen? Haze lah. Right? Are you guys old enough to remember how bad was the haze in 2015? Yeah, it was bad, right? It was bad, right? Like the sky was just brown, right? Yeah. So that whole thing, right? Everything is smoke particles suspended in the air. Okay? So I'm gonna ask you this, okay? What is a smoke particle? Is it a gas? It's not. So what is a smoke particle?
It's dust.
Yeah, it's a piece of ash. Yeah, you're right. Okay? So smoke particle is basically you burn stuff, you get ash, right? You make the ash very, very fine and you spread it in the air like this. That's a smoke particle. So a smoke particle is a tiny, big, I mean, it's a tiny particle to our eyes, but in terms of molecules, it's actually a big chunk. Okay, so when you look at the microscope under, right, under a microscope, right, if you can see a smoke particle, I would expect a smoke particle to be like some oddly shaped piece of dirt like that. You get this? So a smoke particle is what? Is a solid chunk, right? It's not at the molecular level. You can see it. Okay, but it's very, very fine ash. Okay, so smoke particle, right, is just ash, right? It's very fine ash. You understand this? Right, smoke particle is very fine ash. Okay, so for a smoke cell, the extra thing is this: they have a lamp and they focus the lamp into a certain point, right? They beam the light in. Basically, they illuminate the smoke particles. So these smoke particles, you can't, like, it's very hard to see them because they're very dim, right? So what happens is that they look like bright specks of light. So the smoke particles that's been illuminated, they look like bright specks of light. And then these bright specks of light, what are they doing? They are also moving around. What are they doing? What are the bright specks of light doing? Continuous random motion. I will refrain from the word constant because in kinematics, constant means what? Constant means non-changing, right? That's why I use the word continuous here, right? Some teachers are very particular about this, especially the O-level teachers, okay? Which is basically almost all of you here. All right, so just take note of this, right? Notice how I use the word continuous, okay? The words have been given to you. Lift it off my passage. This is not English. You don't have to rephrase. Okay, continuous random motion, right? Just lift it off, it's fine one, right? Don't need to rephrase, right? I have had one student before, oh, I thought we were supposed to read this, understand it, and then rephrase it in our own language, right? No, You're supposed to just copy this wholesale onto your answers, right? Because I've written it in a way that you can copy these answers for your questions. Like it's literally the answer itself. So don't need to go and reinterpret. Don't need to go and rephrase. I want to write it in my own way. I want to use the word constant. How come I lose the mark? Right? I told you already. Okay? So it's continuous random motion. Right? So you can see the smoke particle doing that continuous random motion. You can see the smoke particle being surrounded in a smoke cell. But here's the thing, the smoke cell is a glass box. It's a glass box. Is there wind inside?
Yes.
Huh? I trapped some gas, some smoke into, there's nothing burning inside. Right? It's just that I had something burning, then I use a smoke cell, I catch the smoke and then I put it on the side like this. So the question is there any wind inside? Don't have. It's a completely enclosed glass box. There's no wind. So how come the particle is still moving around randomly like that? So why? Why is it moving around like this? Like this? Guys, come. Come on, you know the answer. The air particles are bombarding the smoke particles. Can you see the air particles? Cannot. What are air particles? Give me examples of air particles. See it?
Oxygen.
Oxygen, carbon dioxide, nitrogen. These are your air particles. There's air particles inside together with a smoke particle. But a smoke particle is not a gas particle. A smoke particle is a piece of ash. Okay? So these molecules are bombarding the smoke particle, causing the smoke particle to move around in continuous random motion. Okay? So what's the observation? What's the observation? The smoke particle is moving in continuous random motion. What's the deduction? It's being bombarded by air particles. What's the next deduction? The air particles are also moving in continuous random motion. 3 points, Brownian motion. I'm done with this part. Okay? Alright, take a quick breather. Yeah? The snacks are, yeah, distribute the snacks. I've got snacks now. I didn't have snacks for a while. Wait, there's a, yeah, pass around, pass around. Don't just leave it there. Nobody's gonna take. Just hand it over to the next table. All right, so yeah, there we go. I can make you write it down though. Yeah, this sorry. Oh. Just pass the packet around. Yeah. If you want sweets, where's the sweets? Huh? No more sweets. What? Where are the sweets? The sweets are there. Take and pass. Take and pass. If those who want sweets, take and pass. Take and pass. I'm gonna have to eat my breakfast. Hang on. Hey, Charlie, what's going on with your sister now? Like what's the competition now? Is it ongoing now? Now. Why does it feel like it's been so long? Like isn't there like an aquatic competition like for the last month, and then now there's another one? What was that? And then the upcoming one is what? Oh my God. Okay. How long is this competition? This whole competition? It's a different competition. Oh no, because I was asking your mom because my nieces want to go and watch the aquatics, the acrobatics. Watch review. I hand off my nieces to you. You go sit there. Yeah. So they want to go and watch. I mean, I'm not interested in all these kind of things, right? Like they are doing like ballet and all that kind of thing, you know. So they like, you know, oh, they like to see how people dance in water. Sorry, I didn't mean to roll eye at your CCA, but yeah, you know, it's like, oh my gosh, like okay, fine. And then they start talking about it. Then they wear their little. I got two boys. I have two nieces. Like I think I'm quite happy about starting with my two boys. Huh? What? No. Wait. Male synchronized swimming? I didn't know that. Do we have that in Singapore? Do we have male synchronized swimmers? Don't have, right? No. Okay. I know male ballet dancers, they're okay. I don't know about that though. Maybe it's a thing. So the next one is the one that you know, there's a big competition, right? It's like the international competition, is it? Also, the recent one is the one where even Benjamin Tan, the year four, Benjamin, Kobe, right? Then there's Isaac Ong, right? Then there's Ifan from year five, YIFAN. Anyway, he's year five. But yeah. I mean, I have quite a few swimmers with me now. Yeah. So apparently, I skipped a year of swimmers. So the previous batch, I had a lot of swimmers with me also. Then I skipped 1 year because that batch of swimmers all took bio. Then now I have the swimmers again. Yeah, the year fours and year fives. It's quite funny. I've had swimmers with me for the longest time. National swimmers, school swimmers, and all that. I don't know why also. Right, it's a thing. Like the first few batches were this bunch of guys called the Cher brothers, CHER, and Bertrand Cher, Bernard Cher, so yeah, 001 yeah. But they were national swimmers. Yeah, they were national swimmers. As in like they were national swimmers, but they retired lah. They retired when they were like 18, 19, that kind of thing. Right. Fulfill the school requirement already, then they just drop. Huh?
18, 19.
Retire?
Yeah.
No. Once they're done with their fulfillment for their resume, they stop right for what? Because the next thing for them is army, right? Unless they want to swim for army. Yeah, unless they want to swim for army. Or you want to play for army also can, right? You can play a sport for army. It's shook like the life. Damn shook, no, 9 to 3. 9 to 3. Then after that you book out already. You go for training 9 to 3. Huh? There's no real army training for these sportsmen.
Why?
You have to be good lah. But yeah.
Alright. Well, I start to join the
Don't need to. I mean, you will go through the BMT, but after that is you're just playing for the army already. Yeah. Okay. All right. Back to business. So there you go. This would be Brownian motion, right? So just remember, one observation, two deductions. One observation, two deductions. Don't kill the fella lah. Do it outside, so that I don't have to claim my insurance here. I want you to. We're gonna learn this thing called internal energy. We're gonna learn this thing called internal energy of a substance. But I won't do it now. Okay, I won't do it now, because I mean, I'm just getting a sense of how you're understanding this and how your school's pace and all that. Because of your school's pace, I think I won't do this now, right? Because there's no urgent need for me to go through this now. Usually, by here, I'm already lagging behind the school's pace. But your school is gonna catch up to me in two weeks time, right? This is term 3 already. So I'll go through this later. This will be incorporated later to thermal properties. Someone said what thermal properties? What the graph is it? The graph, right? The graph going up, down, kind of thing, right? So that will be included in thermal properties. Okay. Okay. Let's do the correct thing first. So we'll just move on to the next one here. Okay. Gas pressure. Pressure. Did we do pressure already? Yeah, we did pressure already, right? Like what was that pressure about? Like what were the formulas for the pressure over there? What? Hello, wrong formula. Yeah, P equals to F over A, P equals to H rho G. So there was a chapter on pressure, right? There was another chapter on pressure where we had P equals to F over A and P equals to H rho G, right? I'll write it down now in case you can't see it. P equals to F over A, P equals to H rho G. Okay? So, this is SLS for you, right? Right? Is the teacher going to go through? What, sorry? No one has taught this chapter yet. Nobody, she can see people logging in to watch it and then click the checkbox to say that you have watched it, is it? That's why, yeah lah. Yeah, so nobody did it yet, so that's why she's like, so what's she gonna do? You done this, right?
Yeah.
In school, you? Right, everyone done this, right? Or doing? Or you haven't yet? Work energy power now. Okay, so this is upcoming, right? After work energy power. Okay, the rest of you done this in school already, right? Oh yeah lah. So you're doing pressure now. You're doing this one now. Okay, good. Right. This one is for what? What kind of pressure?
Atmosphere.
No. Not bad. What does that mean?
Liquid.
Okay, good. So this is for liquid pressure. I was like wondering, you throw big words at me. I was like wondering, do you understand or not? Hydrostatic. Okay, yes, you're right. Okay, so it's liquid pressure, right? Liquid and what?
Yes.
Nay.
Solid.
Huh?
Solid.
Yeah, solid lah. Because he said gas, I said no, then you say solid, right? Yeah, this is for solid pressure. Okay. So the thing is that chapter, right, that when I was teaching you, that was for solid and liquid pressure. I mean, do you remember? I place an object on the table, then ask you, how much pressure does our object exert? Right? Then you use F over A. Then I give you a liquid, I give you a column of liquid, right? I give you a column of liquid like that. Or maybe I invert this into a basin, right? Then you have a barometer like that, right? Then I ask you, I mean, you say atmospheric pressure, but you say atmospheric pressure. No, it was you.
Me.
It was you. Okay. You say atmospheric pressure. You're not wrong. Okay. But the thing is this. We are using the liquid pressure to tell what's the atmospheric pressure. So essentially, we are still looking at the liquid pressure, correct? And that's H rho G, isn't it? Right? Height of the liquid, density of the liquid, then times G, correct? So you realize that none of these two equations here help you calculate
Yes.
gas pressure. Good. Right? Okay. So guess what? Sorry, lame joke, okay? Right. You have to learn gas pressure here. Can? But there is no equation. There is no equation. There is actually there is. There is an equation, but it's not supposed to be in syllabus anymore. However, because of your homework, your school sent that homework, right? I was doing that. I was like trying to answer you that question, the homework question, right? Then it's in the Marshall Cavendish workbook, which means that the rest of the nation, every Singaporean student, has access to that workbook, be it IP or O-level, right? I mean, IP also have that workbook, right? The Marshall Cavendish workbook. You know, your Marshall Cavendish textbook comes with a workbook with practices inside. Do you have a textbook? You have a textbook, all right? Yeah, MGS IP uses the Marshall Cavendish soft copy textbook, right? Yeah, then you have a workbook also, what? You don't have a workbook? TYS? Oh, lagi worse. Okay. But anyway, so everyone has their workbook. Everyone knows how to do that question that I was talking about. So no choice, I have to show you how to do that question. Okay? Alright, because I don't want to disadvantage you. I don't want to tell you that, oh, it's not syllabus lah, don't need to know. Then everyone else knows but you all don't know. Correct? So I have to one up you all. Right? We will do that equation, but technically speaking, the equation is not in syllabus. According to the O-level syllabus, it's written there. It's not, I mean, it's literally not written there. Which means that you're not supposed to know that relationship or the equation. But I'm going to teach it to you anyways. Okay, huh? But before I show you the equation, we're going to learn this first. Okay, we're going to learn this first. Okay, so pressure of a gas. How does a gas exert a pressure? How does a solid object exert a pressure? How does a solid object exert a pressure anyway? How does a solid object exert a pressure, guys? This is a solid object. How does it exert a pressure on my hand? It exerts downwards, it has weight, right? It has weight, so it exerts, but it's divided by the area, right? Okay, so this is considered what? Maybe this is a certain pressure. What if I lay this object on the side?
Lesser.
Why lesser?
Because the larger.
The area is bigger, right? Is it right? P equals F over A. Can you understand, right? So if I place it like this, it's high pressure. If I place it like this, lower pressure, right? Lesser pressure. So pressure is exerted when you have a force acting on something, right? So how does a gas exert a pressure? How does a gas exert a pressure? What are the gas particles doing?
Continuous random.
Excellent. This is called learning fast, right? So the particles are moving around in continuous random motion, right? And what do they do inside of the container? They collide. They collide into the walls. So what we see here is all the particles colliding in the walls, right? They are knocking into the walls here and there, right? You can't really hear it. If you hear it, it will be a nightmare, right? Bing, 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 right? Yeah, okay, you can't hear it. So the particles are colliding with the walls. You understand this? Yeah? And since they exert a force on the walls, there will be a
What?
there will be a pressure lah, right? Can you hand me the container there with the cap? Yeah. Hand me the container with the cap. And pass it over here. Need to empty all the contents first. Wait. Yeah, I should get rid of these packets. Okay. Primary school question. Is this container empty?
No.
Why?
Because ants.
How do you know there's air inside? See, primary school didn't ask you that, right? Yeah. That one's nice. That's the I only like to buy their sweets because that's the natural color sweets. Right? Because I don't want to poison you with Skittles. You all know, right? Skittles have a very high coloring content, and that coloring is like cancer causing. So I buy those kind of sweets for you all. Right? And then as per all my batches, everyone always takes the other colors except the green ones. It's supposed to be a sour sweet, right? Why don't you take the green one? Every time I got leftover green ones. Anyway, so the container, is it empty?
No.
No, it's got air inside. Okay, so that was something that you memorized from primary school. Now I'm gonna ask you, how do you know there's air inside? How do you know there's air inside? Okay, so to answer the question, I'll go through something else first. Right? Obviously, there's air inside. Okay, there's air inside. I'm going to try to simulate the air particles inside by putting some balls inside it. Yeah, balls. Yeah, okay, there we go. Okay, by our theory, that what you just said just now, by our theory, right, what are the particles inside doing? Right, so it's moving in continuous random motion. Okay, so basically the particles are colliding with the walls, right, and it's exerting the pressure where? The inside, right? On the inside of the walls, right? Correct or not? Yeah? You apply a force, you exert a pressure because pressure is force over area. So where's the area? The area is on the inside. Okay. How about the outside?
Yes.
Huh? Yes, what? So you're saying that outside of this container, I close the container. Are you telling me that outside this container, there's also air particles colliding with it? So he's suggesting that on the outside, there are air particles colliding with the outside of the walls. Is he real or not? For real or not? He can see the air particles, man. How you know?
Theory.
Theory. No, the fact I'm breathing, I'm alive. There's air particles. If there's no air particles outside here, I would have been dead already, right? I would have been dead already. So there's air particles on outside. Okay? Right, so do the air particles outside exert a pressure on this side?
Yes, yes.
Yes, right? Can you see it? Cannot. So how do you know? You infer, right? Or you just believe lah. Have faith, right? Okay, so particles collide on outside. Okay, and the particles collide on the inside. Then, now imagine there's absolutely no air inside. Right now I tell you there's absolutely no air inside. How do you ensure that there's no air inside? What do you have to do, guys? I give you a container. There's absolutely no air inside. How do you ensure? How do you make it that there's no air inside? What do you have to do? You have to vacuum it out, right? So you have to put a small little tube, pump out the air, use a motor, zzz, pump the air out, pump, right? So what will happen to the number of air particles inside? Less, right? What will happen to the pressure exerted on the inside? Lesser, right? So you know what's gonna happen? The outside pressure, does it still exert?
Yeah.
The air outside is still breathing, right? We're still breathing, right? So there's still particles colliding outside, right? But inside, got anything colliding?
No.
Don't have, right? What will happen? The whole thing will get compressed in, it will implode inwards. I mean, this is a fairly soft container, right? So if you suck the air out, the inside pressure will be less. The outside pressure will still remain as atmospheric pressure. So is there a pressure difference?
Yes.
What happens when there's a pressure difference? Like the submarine, like yeah. Do you all read the news about the submarine Titan? Yeah, no, not just sunk. Yeah, the billionaire submarine. Yeah, the one that's not only just sunk. What happened? Everything got crushed into a size of a can. No? Yeah, go Google it. Yeah, that's right. Right. Submarine Titan. It's called Titan some more. You know why? You know why is it called Titan? Because that submarine was meant to go and observe the sunken Titanic. That's why they call it the Titan. Right? It was badly designed. When it reached a certain pressure, everything got crushed, including including everyone inside. So at first, right, they thought that the thing sunk and landed on the bottom. They thought that the structure was still holding, right? And that the people are trapped in there and they tried to rescue them. But in fact, in a split second, everyone just got crushed immediately. So they died a very instant death. Like, that's it. Huh? I don't know about that. I don't know whether it's painless. At least it's short term. Okay? Alright. And how do they know that it was instant? Because there was a nearby US submarine that was spying the waters around, and they, from the sonar, they can hear that the submarine got crushed in an instant. So there was no way there was any survivors, but they couldn't announce it, because if they announce it, that means they announced it that they were there at the time. Then they say that, you know, they after they did some security briefing, they declassified it and they say that, oh yeah, we were there. Anyway, so if I vacuum pump all the air out from inside, right, will the pressure be higher than the inside pressure? It will be, so everything will get crushed, right? So now back to my question, Endo.
Yeah.
Okay. How do you know that there's air inside?
Because it's not.
Yeah, it's not being crushed. How do you know there's air inside? Because it's not being crushed. If it was being crushed, then that means the outside pressure is greater. It would have been crushed like this, right? It would have been compressed. Now, do you realize that you do this almost every other Chinese New Year?
Huh?
You know, when you go and visit Chinese New Year, right? You take the Yo's packet drink and then you drink the drink, right? Then you drink, continue sucking, what happens to the packet? Yeah, it gets crushed, right? It gets crushed because you're sucking the air out, and the atmospheric pressure is greater than the pressure inside, so now it's being compressed. Okay, so I chose this container, right, and not this one. right? Because this is absolutely rigid. If you vacuum pump it, it's not going to change shape, so you won't know whether there's air or not. That's why I chose this one, because this one is slightly elastic, like this. Okay, it can be slightly like this. So back to my question: how do you know there's air inside? It's basically it's not expanding nor is it being compressed, right? It's not like bloating out. It's not, right? So what does this tell you about the pressure inside and the pressure outside? It's equal, right? So what pressure is it?
Yes.
Like what is it called? I mean,
Atmosphere.
atmospheric pressure. Okay, yeah, right. So your job now is to explain how the particles exert a pressure inside. Okay, and you do it by 2 steps only. Just 2 steps, right? Just 2 steps. They ask you for 2 marks. Explain how a gas exerts a pressure. Yeah, 1 step. Gas molecules are in continuous random motion. 2 step. They collide with the walls. They exert a force, right? Since pressure equals to force over area, there's pressure exerted on the walls. Okay? So please understand that when you say this, it doesn't mean that the inside pressure is greater than outside. What they are not showing you here is that the atmospheric pressure is acting on the outside. So it's not like the container is going to bloat outwards, right? It's not going to expand like a balloon. Okay? So you see this container is not bloating, right? It's just the same pressure inside and the pressure outside is the same. Can. Okay, so 2 marks. Explain how a gas exerts a pressure inside a container. You said that the gas molecules are moving in continuous random motion. They collide with the walls. They exert a force, right? And then since there's a force over area, a pressure is exerted. It's basically exerted on all sides, right? It's exerted on all sides. So, if you want to, please draw this in. Yeah, good. All right, I see some of you sketching this in. Right, pressure here, pressure there, like this. Right, that's the learning part. Oh, the other day there was one student who asked me, because at the IB level, all my notes got a lot of IB and JC level, my notes got a lot of blanks. Like I keep big blanks there, right? Because I want the students to draw the diagram and all that. So the student was asking me, this new joiner, doesn't know anything, asked me, how come your notes all got so many blanks one? Right? Is it because you're trying to gatekeep it? Yeah, gatekeep, I said, dude, if you really want, right, you can just go to Popular. I give you this title, you go and buy the title. That's a guidebook. JC got guidebook, IB also got guidebook. You buy the guidebook lah. All the details that you need are there. Actually, you don't need my notes one. Yeah, it's true also. You go and buy a guidebook, you can see all this also. You go Popular. What are these special are these ninja notes? Right? Nobody in Singapore gets it. No, you just go and pick up the guidebook, you can see the exact same thing here. Yeah. So what's my value at? My value is making you write all these things. My value is making you draw all these things out. Right? Write down this, draw these things out here like this. Right? You know why? Blame Harvard. So 6 years ago, right? I watched a web conference that time COVID, right? So I watched a web conference on like how Harvard teaches and how Harvard like encourages their students to how they learn, right? And one of the key things is there's no right brain, left brain nonsense. There's no auditory, visual, kinesthetic nonsense, right? How you learn is basically you write and you draw and you recite it out. Those are like the old. There's no, our technology has evolved, but our bodies haven't. So all the things that we've been doing before, writing, reciting, and drawing, have always been the classic ways of learning, right? And Harvard says that that's the correct way of learning. Yeah. Oh, you're gonna watch all these YouTube telling you that the old ways of learning are now very old-fashioned. Now's the time you learn, right? Your what was it? Your customized way of learning. Go and read the book about swimming. Then go and swim. Yeah, I can learn how to swim by reading. Let's see you try that lah. All right. So my point is, because of that conference that they held, and because of all the other videos I've watched so far from some neuroscience researchers, I make you draw so that it will learn in your head. If you don't draw, you're not learning. It's just as simple as that. If you don't write down the things I tell you, you're not learning. If you just sit there and you stare at me, right, like some Netflix show like that, you're not learning. You're just watching a show. Okay? Right? So blame Harvard, huh? Not my business. I just took Harvard's advice and I apply it to you. You want to think that Harvard is all full of shit? Go ahead. Right? I believe Harvard has a good record of producing very smart students. Okay? Right? But smartness is trained. It's not born. You're not born with smartness. You're trained to it. Right? And how you train is how you deal with like these things here. Right? I show you a diagram. Do you draw it out? Right? Do you copy it down? These are the small things that will build on your smartness. It doesn't show that you're smart. It doesn't show that you're dumb, right? But it really builds on it. If you're not building, then everyone else will catch up on you. Okay. So there we go. There is one interesting note. I'm gonna just finish up today's lesson with this. There's one interesting note that the pressure depends on two factors. Right? Pressure depends on two factors: the force of each collision and the frequency of collision. So this is like we're going towards a really important part now. So the pressure depends on the force of each collision and the frequency of collisions. Just multiply to each other. So each collision is how much force. Then you multiply it to the frequency of collisions, like how many collisions per unit time. Right? That will give you the total pressure that's acted inside, the total force, and therefore the total pressure that's acting inside the container. You know what I'm saying? Okay, what does the force of each collision depend on? Like, how does the force of each collision, like, what does it depend on?
The weight of the gas.
Oh, not bad. Okay, so there's a factor there, but we don't really care about molecular weight, right? Because we're doing physics, not chemistry. But you're not wrong, right? So that's one factor. But any other factors? How much force does each particle collide with the wall?
Speed.
Yeah, the speed. Right, so that's one important factor. So the speed of the particles will affect the force of each collision. The faster the particle moves, right, the more force it exerts. In fact, Enzo, sorry, if let's say I'm looking at a particular gas, right, the mass of each particle is the same. So it's not like I can compare between different masses, right? So essentially, the force of each collision is solely dependent on the speed. How about the frequency though?
How many particles?
Good. So if you want more frequent particles, if you want more frequent collisions, one of the ways is to increase the number of particles. Like you add more particles in. Okay? You add more particles into it. But you keep the area the same. That means you keep the container same volume. Right? So you use a rigid container. Right? So if you want to increase the frequency by adding more particles, you must use a rigid container. Like whatever you can do to increase the frequency lah. Right? Any other ways of increasing the frequency of collisions? Any other ways of increasing the frequency of collisions?
Maybe like smaller.
Oh, you want to make the volume smaller? Yeah, absolutely, yes. Yeah. No, don't worry. My face here, this is a very bad case of RBF. Right. So like my face looks like I'm scowling at you. I'm not. Actually, I'm smiling, but my cheeks are just sagging a bit, so you can't see the smile.
What?
Anyway, no, I'm serious. I'm not giving you a black face. No, I'm serious. Like a lot of people misread my face. That's the problem. I'm just telling you. I was just telling the other class also. Okay, I just didn't get enough sleep last night. It's about 5 hours, so that's why my face is little bit droopy now. So, frequency of collisions, yes, you can. You are right. You can also compress the gas. You can give it a smaller space. If you give it a smaller space, then the frequency will definitely increase, right? Okay. Anyway else? How about increasing the speed?
Yeah.
Also can. You also can increase the speed to increase the frequency. right? So if the particles move faster, they'll collide with the walls more frequently lah. Can? Okay, good. Because this is scenario time.
Yeah.
Huh? Scenario time. That's a gaudy looking thing. Okay, rigid container. Rigid container.
Shit.
Okay, rigid container means what? Means volume cannot change. Volume cannot expand, right? Okay. I got some particles inside. Okay. Let's say I got some particles inside. Yeah, it's not in the notes. You have to draw it out. So I got some particles inside. I'm gonna heat the gas. Oh, I'm gonna heat the gas. I'm gonna give it heat. Right, Bunsen burner, heat the gas. Yeah, go ahead. Right, so you get heat the gas. Okay, tell me what happened to the particles. Okay, by the way, what particles are these?
Yeah.
Gas particles, air particles. Okay, can. Right, that's fine. Right, can you see them? You cannot see them, huh? That's a trick question. Right, so these are gas particles. Right, it's just that in my drawing, I draw it. Okay, so just take note that you can't see it. Both empty, yeah. I thought I had it. I thought I opened it already. Oh, oops, yeah, empty. Use eat the crackers. I'm sorry. Yeah. Hey, what happens to the gas particles then? When you heat it? Like when you give it heat. Huh? What? Move faster. Right, like Simba's dad. Move faster. Right, so KE increases. Y'all don't watch Lion King, man? Lion King? What did Simba tell his dad when the stampede was coming? Move faster. Okay, never mind. Y'all nowadays y'all don't watch the same things anymore already. Diversion of culture. So when you supply heat to a particle, the particle will increase KE and therefore it will move around faster, right? So it'll go faster, the speed will increase. Huh?
Wait.
Let me put you in a frying pan.
Oh, then how right?
Yeah lah, same lah, same. Okay, alright, you see a lizard or hot stone before? Alright, same. Okay, alright, so yeah, there you go. So you know when you supply heat to a particle, the particle will move faster, the K will increase. So what will happen? What will the particles do?
More frequency.
They will collide with the walls more frequently, right? They will collide with the wall more frequently and yeah, more forcefully also. Okay, so once the K increases, the particles will collide with the walls, right? More frequently and more forcefully. More frequently and more forcefully. Okay, tell me what happens to the pressure inside. Yeah, pressure inside will increase. Right, the pressure will be higher. Higher pressure. Okay? Am I allowing the gas to expand? No, right? So is the inner surface area still the same? It's still the same, right? So if you have more force, right, P goes F over A, right? If you're telling me that I have just increased the force, but the area still stays the same,
Yeah.
then pressure increases. Right? There you go. So gas particle, right? Yeah. You understand this?
Yeah.
Right? This is us increasing the gas pressure inside by heating it. Okay. Hang on, Anybody started doing chemistry? This thing called reaction kinetics, kinetics already? Kind of like rate of reaction. Anyone? Chemistry? Rate of reaction?
Yeah, I think.
Rate of reaction?
Yeah.
I think your school is a bit fast, but okay. Rate of reaction? No? Anyone? Rate of reaction? No? Are you guys at the same preparation of salts? Acids, bases? Oh, mole. Oh, that's slow. That is slow. That one is slow. July, you're still doing mole concept. That is slow. No, why? Then the first 6 months, what were you learning, Nicola?
Well, she finished teaching everything about she just finished.
Oh, what the heck? Done what? Have you done chem bonding?
Yeah.
Preparation of salt?
Then do it.
Acid base salt?
Yeah.
Okay, no, okay lah, still not so bad lah. But more you just started on more concept.
We are.
Oh, hey, July leh, hello. Okay, Oh, term 3 already, what you all doing? Okay, anyway, yeah. Later on in chemistry, in this chapter called rate of reaction, right? When let's say, for example, an alkali molecule reacts with a acid molecule, for example, you've done acids and bases already, right? Okay, then we have to talk about the molecules colliding with each other. Okay, to have this thing called effective collisions, to have this thing called successful collisions. Okay, those are not related to this. That's intermolecular collisions. We are not concerned about that here. Right? How is the pressure exerted again? The molecules are doing what? They are colliding with what? The walls, not other molecules. I don't care about that. They do, but I don't care about that. I only care about what they do to the wall. So as the particles collide with the walls like this just now, like this, the two particles collide with each other, yes, but does that help to increase the pressure? No, that doesn't help to increase the pressure. It's only when it collides with the walls. Sorry, what? When the two particles collide with each other, like that is not part of this concept. Like you see, got two gas particles, right? They move around randomly, continuously. Right? Do you think there's a chance for them to collide with each other? There is, right? But does that contribute to the pressure? No, it doesn't. So what's the thing that contributes to pressure? When the particles collide with the walls. When the pressure collide with the walls. Then that's pressure. You understand this? So talk about the particles colliding with the walls, because later on in chemistry, very soon actually, I think towards the end of term 3, you will start learning this thing called rate of reaction. And then you will start learning this thing called effective collision between particles. Particles must collide with each other. That's none of physics problem, right? Physics is about colliding with the wall. Are we okay on this? Can I? Okay, good. Right, so common mistake, molecules collide with other molecules to exert pressure. Like that's a really common mistake. Like we get that, I get that all the time. Let me do another scenario, come. Let me do another scenario. Again, rigid container. Right, I'm gonna have a rigid container here. Okay, it's a rigid container. Right, now I'm gonna pump gas into it. So I have a gas pump like that. So like this, right? So you can see this is like your bicycle foot pump, right? You pump gas into it. So you kind of like inject, right? You inject extra molecules, more gas molecules. Okay? You inject more gas molecules. So describe what happens inside. What happens on the inside?
It's more pressure.
But why?
Because it's more.
So more particles will lead to what? More particles will lead to higher frequency of collisions, which will lead to greater force and hence greater pressure. Understand? Hey, what is different from this and the one before?
One is.
What's different?
So
Yeah, the previous one they move faster, right?
speed.
This one? Did we mention about the speed?
No.
No, right? There's no mention about them moving faster. So what's happening to the particles? The particles are, there's just more particles. More particles, they collide, right? And therefore the pressure is higher. Then, yeah, that's pretty much it. That's like more particles, higher frequency of collisions. Yeah. So don't try to okay, you have to figure out, you have to realize that when I want to talk about pressure, I need to talk about the force of each collision and the frequency. So you got to try to make sense. Adding more particles will increase the frequency, but it doesn't increase the force of each collision. But overall, you still get more collisions. And more collisions just means total greater force, right? Greater total force, and therefore the pressure is higher. Okay, Yeah, that's pretty much it for this part here. Okay, hang on. Okay, that's pretty much it for this part here. For all the O-level students, like this chapter ends here. Yeah, yeah, this chapter ends here. Hang on, this chapter ends here. So there's this part at the back, which I will require the IEP students to check against your syllabus to see whether or not this is included in your syllabus. Because I'm not sure, because with the recent change in the last 1 year, the O-level students, these next few parts have been all taken out. Okay, they've been all taken out. So like technically they don't need to do all of this, right? All these equations, all these relationships, all the graphs and all that, right? But some of the IPs still have to. So I need you to go and check. You need to double check against it. But I will now end off with this. Okay, so I'll now end off with this. So at the end of the day, this chapter at the end of it is this equation P1V1 equals P2V2, right? This was the equation that I mentioned in the group chat. I don't know whether you've seen the group chat. Did I send out a picture on the group chat for that thing there? When did I last send out? Well, when was it? It's quite long ago, is it? No, it's not. It's not that long ago. Sorry. Just give me about 10 more minutes. I'll be done with this. Yeah, there was this question. So I was notified that this came out in the Marshall Cavendish workbook. This one here, this question. It's a bit faint, sorry, but I sent it out before. So there's a tube, there's a thread of mercury, there's some trapped air inside. Okay, right? Then they held it horizontally and they held it vertically and they held it like upside down and all that. Right? Okay. So do you understand that this is in the Marshall Cavendish workbook? Do you understand that every secondary school student in Singapore has the same workbook and they also are doing the same question? Okay, right? And also at the same time, I think none of them get it, right? Because this thing here, the concept here, where's this question located at? Is it in the pressure chapter? It's on the pressure chapter, right? Do you notice that I mentioned like very clearly that in the pressure chapter you only learn this and this. There was no gas pressure, but gas pressure only came in this chapter, kinetic particle theory. This one here. Okay, so there you go. So this question, if you all can see the question here, I have described it in a prior video before. Hang on, let me just show it to you first. I've done this in the previous video before. Hang on. Where's that video? Yeah, this one here. I sent it previously before. This one here. Okay. Understand the mercury and air column in tube concept, right? And then I said like, yeah, there was this picture here and this one. It's the same thing, right? I did this when I was in I sent this out when I was on leave. Okay. So I have limited access. I can send you this concept here. So, right. So the question is there. But before we go through that question, right? I mean, I'll do it again. Don't worry. Right? I'll do it again. I mean, if you don't want to watch the video, I'll do it again. Right? This I think is a fairly difficult concept. Let's understand this first. You see the air bubble at the bottom? Right? It's at the bottom of the lake. There's an air bubble, or you could be a swimmer. Right? You swim down to the depths there, and then you let a bubble out. Okay? Right? And then there's an air bubble. So the idea here is that as the air bubble rises, it begins to get bigger and bigger. Why? Yeah, you all understand this intuitively. Right? So one more time, as the bubble rises, right? As the bubble rises, it's basically receiving less pressure. You should understand, right? H rho G, right? So if you're deep underwater, the pressure is high, right? I mean, you're done swimming before. Have you all gone underwater and you all feel that your ears are being pressed inwards? You have, right? Right. That's air pressure, right? So that's air pressure. So as you go higher and higher up, you will receive normal atmospheric pressure, right? So are we all okay on this? Bubble is small under high pressure. Bubble can expand when the pressure is less. Okay? What's the pressure up here? What's the pressure up here?
Atmosphere.
Atmospheric pressure, right? It's atmospheric pressure because it's near the atmosphere, right? So it's atmospheric pressure. So atmospheric pressure. Okay. How about the pressure down there? So it's due to 20 meters of water, right? In a sense, right? It's because of, so it's higher. So in the question, you're not supposed to know this, so they'll tell you this. If 10 atmospheres, sorry, 10 meters of water equals to 1 atmosphere, right? How many meters of water is that? 20 meters of water, 20 meters of water, right? If every, this is given in the question, so if every 10 meters of water is 1 atmosphere, how much is the pressure at the bottom? 3 atmospheres. Do you understand why? I mean, I'm just aiming this at you because you're a swimmer. But I mean, actually, more should be her, right? It should be, like, you go into the water deeper than her, won't you? Like, she's always almost on the surface only. But you're like, somehow your head is all the way down there, right? Okay, so yeah, right. Here's the thing. So the pressure at the bottom of the lake is the 20 meters of water, right? 10 meters of water is 1 atmosphere, so 20 is 2 atmospheres plus the atmospheric pressure pressing down, so it's 3 atmospheres. Okay, so in that question that was in the workbook, is written, they slip in a note. They slip in a note. I don't know whether you all noticed this. It was very sneaky of them, right? It's quite nasty as well. Quite hated them for that, right? They sneaked in a small little tiny note. Let me try to zoom in, see whether you all can see it. Oh goodness, I cannot see. Right. So you know what? I'm just gonna paste it here. I'm gonna zoom in here for you guys to see. What does it say? There, you see? If temperature does not change, the multiplication of pressure and volume of the trapped air is a constant. Right? This used to be part of the syllabus. It was taken off syllabus, and what Marshall Cavendish did was that they amended the question like this so that it's still doable by the students. Not fair lah. But then again, why am I going through this? Because everyone else in Singapore has this workbook and everyone else is doing this question too. So it's my obligation to do it as well. I'm not going to tell you that, yeah, surely it won't come out one. Your teacher said the exam how? Can I control? I can't control, right? Then you fail your exam how? It's my fault. So I have to make sure that you know how to do this. So basically, it's just trying to say that P1 V1 equals to P2 V2. That's what it means. Okay, which means that for this air bubble, where's my air bubble? For my air bubble here, as this air bubble is rising, the pressure will change, the volume will change, but it changes such that P1 and V1 at the bottom is equals to P2 and V2 at the top. Right? So you take P1 times V1, okay? P1, V1, and P2, V2. Yeah, pressure multiplied by volume, P and V. Right? I know some of you have not done pressure in school yet, so that's why it's a bit like, strange to you. But I'm showing you this. So the air bubble is not a rigid container, so it can expand. So it expands because there's lesser pressure. So as it rises, right, the pressure will change, the volume will change. But the concept is that the P1 times the V1 is still constant, right? So the P2 times the V2 is equals to P1 V1. So you will write this down. P1 V1 equals to P2 V2. How much is P1 at the bottom? 3 atmospheres. I'll just put it as 3 because it's a ratio question, right? I'll just put it as 3. What's the volume at the bottom? 4 cm cube. What's the pressure at the top? 1 atmosphere. So what's the final volume at the top?
12.
Yeah, 12 cm cube. That's all. That's basically what you're supposed to do. That's all. You're just supposed to find a ratio to find the volume. There's no complicated physics here or no complicated math here, right? There's no like quadratic or like some function or something like that. No, it's not that. It's just simply, right, telling you that, right, for that question, the Marshall Cavendish workbook question, the P1 and the V1 multiplied to each other is equal to the P2 and V2 multiplied to each other, right? That's why you need to do like, you know, your schoolwork, and that's why you need to do the practices so that I can like kind of like get a sense of like, I mean, I don't bother buying the Marshall Cavendish book, like I know it's a scam, right? It's a scam. It's a scam, right? They have a complete monopoly over the whole of Singapore, right? They come out. Do you know how many books they sold or not? Oh, freaking tens of thousands, eh! Like the profit from each book, how much you get every year? Tens of thousands, you know, dude. It's a scam, man. And what did they do when the syllabus changed? They just change the question and say that, oh, just assume that P times V is constant. Then they say, oh, still in syllabus. Huh? No, it's been taken out. But no choice, I have to go through this still. Okay? Now, of course, there's a much deeper understanding for this one. Like, I can go on and go and teach you. Like, to understand this, right, I have to go through all these parts here. This part here, this part here, this part here. But that's what I'm saying, that for the O-level syllabus, it's been taken out. Most of you are O-levels, so I need the IPs to check. Right? If it's still in syllabus, if like Chow's law, Boyle's law, and pressure law is still in syllabus, right, I'll see you separately for it. Okay? Right, I'll see you separately for it. So take these words down: Chow's law, Boyle's law, and pressure law. The rest don't need, only the non-express ones. Chow's law, Boyle's law, B-O-Y-L-E-S, Boyle's law, right, and the pressure law. If you see these three names in your notes, let me know. I'll see you separately for it. Otherwise, you know, we just do the normal thing. Okay? Right. So next week I'll go through the Mercury question, this Mercury question, right? I mean, but technically speaking, the video has been released already. So if you had watched it, then yeah. But I need you all to do one thing. You all have to watch the latest one I sent. This one here. Like, you definitely need to watch this one. Because there's one kinematics question inside and there's one dynamics question inside. This is already at a higher level of understanding. This is not basic anymore, right? But you have to watch it because this is the type of O-level questions you get. Right? So far I've been training you the basics only, right? At some point I need to bring you up again. Okay? For those who are having a test coming up, do you know where the practice questions are at? In the shared drive? Okay. As you're packing, one last note. Wait. As you're packing, one last note. Okay? Do you all see this folder? Right. This is the year 3 end of year preparation. You go inside it, right? You will see one paper inside. I think I already assigned this paper, right? Does everyone have the printout for this? Huh? I printed it out, right? Does anybody not have this one, the paper one? No? Okay. Can you get started on this? If you have to, just do the first 10 MCQ. Just do the first 10 by next Saturday. 10 MCQ lah. Come on, once you all started doing, you all will finish it one, right? I don't think you can finish it anyway, because it's other topics. But at the last part here, question 20, pollen grains under a microscope. So it's gone to all the, like, it's basically come to the point whereby, you know, what I've taught until already. Okay? So you know what? Okay, let's challenge you, 20 MCQ. Okay, bye. I'll type it down in group chat. Yeah, why? Ask you to do MCQ only, not structured questions.
We give it like last lesson.
I don't